Irrigation Training and Research Center, ITRC, at Cal Poly State University, San Luis Obispo, California, has developed this video to provide information on various filtration methods for drip and micro-irrigation systems. ITRC is grateful to the many manufacturers of filtration equipment which provided information for this video. Of course, illustration of specific brands throughout this video does not constitute an endorsement of any particular brand. Water sources for drip and micro-irrigation systems include rivers, reservoirs, municipal water, canals, and groundwater. Each of these sources may be contaminated to varying degrees by organic and inorganic materials. All modern irrigation systems need to be protected from these contaminants. Filtration for drip and micro-irrigation is a challenge because water quality and the nature of contaminants can change with time. This video will provide basic information on the most commonly used filtration components used today. Keep in mind that a filtration system may consist of several components. For example, at one site, one may use pre-screening, media tanks, and backup screens. Before beginning with the hardware itself, it is helpful to review how much filtration is needed. Of course, filters used in agricultural irrigation do not remove salts, they only remove solids. As a rule of thumb, all particles greater than 1/10 the diameter of drip emitter holes should be removed. For microspray systems, which have shorter passageways than drip emitters, the general rule is to remove all materials greater than 1/7 the sprayer hole diameter. Chemical injection systems are also always needed. Filtration alone is insufficient to prevent emitter plugging by material originating inside the hose. We will now begin with filtration hardware and components. Filtration devices can be categorized by the types of material which they remove. For example, sand separators can remove sand but are ineffective at removing silt, clay, and organic matter. Another method of discussing filtration is in relation to the water source. That is, if it is a well supply or a canal or river supply. Some devices are used on both well and surface water supplies. For example, simple tubular screens are used with both supplies, but they are insufficient as the primary filter with surface supplies. However, they may be used as a backup to a media filter. On the other hand, with extremely clean well water, a simple tubular screen may be the only filter needed. This video will begin with the cleaning of surface water supplies. Remember that well water which passes through a reservoir is considered to be a surface water supply because it is then exposed to organic matter growth. Pre-filtration devices are especially important with surface water supplies from rivers and canals. Most filtration problems with surface water supplies are caused by improper attention to pre-filtration. Without adequate pre-filtration, the regular filters can be overloaded and must be cleaned or backflushed very often. Categories of pre-filtration are reservoirs, a simple bar grill, an improved perforated stationary steel plate, conveyor belt screens, self-cleaning pump suction screens. Reservoirs provide two aspects of filtration. They can be used to aerate well water which is high in iron in order to avoid problems such as seen with this plugged disc filter. And sand from canals settles out of the water, which is very important if the supply has more than 200 ppm suspended solids. Aside from filtration, reservoirs can be very useful in providing a flow rate buffer in case well discharges or canal flows change with time, and in case the drip system flows change when irrigating different blocks or when backflushing filters. Primary design consideration are The reservoir should ideally be long and narrow to allow particles to settle out. The reservoir must also be accessible and cleanable. The reservoir outlet to the drip system should be placed as far away from the reservoir inlet as possible. A simple grill of vertical or inclined bars, spaced several inches apart, is often used as pre-filtration on canals. These grills can quickly plug and may require frequent cleaning, as often as every hour in some cases. In Grand Junction, Colorado, local Bureau of Reclamation engineers developed a new design. It is a long steel plate with 3/4-inch holes. It is designed with an entrance velocity of less than 1/2 a foot per second. This design allows weekly instead of daily cleaning. It is cleaned by using a squeegee. It is quite effective as long as there is a flow past the steel plate. For many installations, a pre-filter design uses a flexible conveyor-type belt. These units are self-cleaning and are very effective for removal of particles with a diameter of greater than a 1/2 inch. As the belt rotates, the trash drops off the belt either by gravity or with the help of a downward pointed spray nozzle assembly. The trash is not only removed from the belt, it is also removed from the water supply. The belt rotates a certain distance on a fixed time interval, or in response to a difference in water levels on each side of the screen. These rotating belts are almost always fabricated locally in a machine shop. They are powered by AC, DC, or hydraulic motors. Another pre-screening device has a specially designed screen cylinder around a pump suction pipe. In this design, the screen itself rotates. Part of the pump discharge water is used for spray water and to rotate the screen. Another design has a rotating sprayer inside the screen. These special self-cleaning screens have diameters as large as 30 inches and can handle flows of up to 2,500 gallons per minute. A winch system is needed to raise or lower the screen to match the water level. Also, it enables the irrigator to remove the screen from the water if it is not being used, so that it does not plug up with stagnant algae. If there is no flowing water, a special structure must be designed so that the trash will not return to the screen in a few minutes. In summary, pre-filtration removes problems which might otherwise overwhelm the regular filtration system. Key types of pre-filtration are reservoirs for aeration of iron and removal of sand, bar grills, which are the least effective, long perforated steel plates, conveyor belts, which are very effective for heavy trash loads, and rotating self-cleaning pump suction screens. Media tanks are the most popular primary filter for very dirty water situations. There are so many important selection, installation, and adjustment details for media tanks that the Irrigation Training and Research Center has developed a separate video just for media tanks. Therefore, this video will only touch on a few items. Media tanks provide three-dimensional screening of materials, as the dirty water flows through a layer of special crust granite. During filtration, an equal amount of dirty water flows through each tank. Dirt remains behind in the top of the media bed. During backflushing, three-way valves on the top of each tank change position, one at a time, shutting off the incoming water, opening an outlet to the atmosphere, and allowing water from inside the tank to exit. Underdrains at the bottom of the tank allow clean water to flow back upwards through the tank. The clean water for backflushing must come from another tank, as shown here with this model. One tank is backflushed at a time. When the media is fluidized during backflush, the dirt which was trapped on the top of the media bed is flushed up and out of the tank. Not all underdrain designs provide for such uniform uplifting of the media bed, as seen here. A mineral aggregate mix is sometimes bonded together with epoxy and cast directly into the bottom of the tanks as an underdrain. This design has the lowest pressure loss and most uniform dispersion of water, but it requires excellent maintenance and backflush adjustment. Some lateral or slotted underdrains are very reliable and also have large open areas. However, there are major differences between various designs and their effectiveness. Special attention must be given to accessory hardware so media tanks can be operated and adjusted properly. The backflush must be adjusted for the correct flow rate, duration, dwell time, and frequency. If the backflush is not adjusted correctly, the media tanks will not operate correctly. Special hardware is needed with media tanks, including air vents, a backup screen, and sometimes a pressure-sustaining valve. In summary, media tanks are very popular, but must be properly selected and adjusted to obtain the desired performance. Gravity overflow screens are popular in some areas. They provide high-capacity filtration for organic and inorganics. Water enters a tank and then flows over a weir onto a tight screen which is slightly tilted from horizontal. The screen is typically 150 mesh and is underlain by stainless steel expanded metal for support. Clean water passes through the screen to a collection chamber where it is picked up by a booster pump and passed onto the irrigation system. This schematic shows that a key element of the system is some type of flow regulator. Typically, flow enters these filters by gravity through a pipeline. If too much water enters, the unit will flood. If not enough water enters, the booster pump will begin to pump air. The best way to control the flow rate is to adjust the flow before it gets into the unit, as is shown here. A butterfly valve on the source line is controlled by a float which sits at the same water level as the water below the screen. Such a desirable float design on the source line is shown on this installation. In some undesirable situations, the water supply sometimes decreases with time. Installers must then place a float-operated butterfly valve on the booster pump discharge. This should be avoided whenever possible because the irrigation system distribution uniformity drops when the pressure is lowered. The screen is kept clean by the vibration of the water on the screen itself, plus by rotating spray wands under the screen. Occasionally, the screen may need to be cleaned using a hand spray nozzle. If this is insufficient, the screen may need to be cleaned with a detergent and soft bristle brush. It can be seen that the screen is self-cleaning. The dirt goes to the far side of the screen where it falls into a collection chamber. This unit has a flow rate of 600 gallons per minute. Water, which also goes into the dirt collection chamber, is continuously removed using a venturi, which return the water to the inflow section. The dirt must be manually removed from the screen and collection chamber about once per day. However, these systems have no backflush water to dispose of. There are several ways to power the spray wands. Here are the parts for a spray wand which uses a gear-operated sprinkler as a drive unit. Some of the pressurized water from the booster is used to drive these sprinkler-based units and the recycling venturi. Another rotation mechanism uses a turbo drive, which uses a small jet of water to turn some paddles. The rotating paddles then turn a shaft, which turns the wands inside the tank. Small overflow screen units are often made of fiberglass or stainless steel. Larger units are typically made of stainless steel. This unit is a double tank and has a capacity of 1,500 gallons per minute of dirty water. The overflow screens are not the best choice if water source is pressurized, because all of the pressure is lost at the entrance to the screen. On the other hand, if water is available with about 4 feet of pressure, these filters have the lowest energy requirement of any high-capacity filter. Overflow screens have advantages in that there is no backflush water to dispose of, and they can handle very high contaminant loads, including algae and sand. Disc filters have been used as primary filters for many years outside of the U.S. and have recently gained popularity in some areas of the United States. The system shown here is a unit with automated backflush. It is capable of filtering a range of flows between 180 gallons per minute to 1,500 gallons per minute. Each disc barrel is composed of a stack of discs. The discs are grooved on each side, with adjacent disc faces having grooves in opposite directions. When pressed together, the discs provide a three-dimensional filtration. Discs can be selected for a variety of filtration qualities, ranging from 40 mesh to 600 mesh. This particular unit has 4 towers with 12 barrels. The dirty water enters the barrels from the outside pipes, and clean water exits through the center pipe. For automatic backflush, a pressure differential switch activates the solenoids shown here once the pressure differential has built up to 7 to 10 psi. The solenoids then actuate a backflush valve, which shuts off the incoming dirty water for one set of barrels. This valve also opens an outlet for the dirty backflush water to exit the system. During backflush, the discs are slightly separated by a special piston in each barrel, and clean water from the center pipe backflushes the discs. The discs are also spun during backflush. The spinning helps to remove any dirt from the discs. A backflush of one set of barrels requires about 20 seconds of flow, plus 10 seconds of dwell time to reset the backflush valve. Therefore, this unit requires 2 minutes for backflushing. Each barrel shown here requires 60 gallons per minute for backflushing, for a total of 180 gallons per minute per tower. In order to have a successful backflush, these units require a minimum of 45 psi during backflush. Since this may be more than a normal operating pressure, automated disc filters either have a special additional booster pump for flushing or use a pressure-sustaining valve downstream of the filter during backflushing. A small 1-inch manually cleaned filter is located behind the pipes here. It is needed to clean the water for the hydraulic actuator for the disc barrels during backflushing. If the filter does not backflush properly, the problem often lies with this dirty 1-inch filter. Disc filters are best for organic matter. Sand tends to stick between the discs and sometimes is not removed during backflushing. Here you can see sand which has moved completely through the discs. If the system is not automated, the disc units must be taken apart, the discs separated, and then hosed off with clean water. Disc filters have the advantage of occupying a small space. Some units also come completely pre-assembled for simple installation. Standard tubular screens are sometimes used with surface water as the primary filter. This is a serious mistake. Standard tubular screens are for extremely clean water situations only, such as downstream of the primary filter. They have only a two-dimensional cleaning surface and plug quickly if the water is dirty. There are major differences between tubular screens in terms of the direction of the flow, ease of cleaning, and construction. Designs should be selected which allow the dirty water to enter from the inside of the screen cartridge, with clean water exiting to the outside. Flow in the opposite direction can collapse the screen. If the fine filtering fabric is on the inside of the screen, the flow is from the inside to the outside. They are cleaned either manually or automatically. The screen should be easy to access and have a slow release lid, as should all filters. Operators should be able to remove the screen without dropping the dirt into the outlet hole of the device. Some manufacturers have a special design which appears to be a tubular screen, but which has an internal rotating self-cleaning mechanism to overcome the capacity problem associated with standard tubular screens. Hydraulically actuated filters have a differential pressure switch. The differential pressure switch reads high pressure, indicated by the blue striped hose, and low pressure, symbolized by the hose with the red stripe. Once a pressure differential of 7 pounds per square inch is sensed, the multicolored button shown here recedes. The suction scanner is hooked to an exhaust valve which discharges into the atmosphere. Simultaneously, the rotating arm or suction scanner is activated and makes one very slow revolution. The suction scanner fits inside a 120 mesh tubular screen. Clean water flows backwards through the screen into the scanner ports and cleans the screen surface. The scanner has only a 1/32 inch clearance from the screen. The irrigation water continues to be filtered during the cleaning process. The filters have a coarse pre-screen, which must be manually cleaned periodically. Here, one can see a manual activation of the backflush. The mechanism on the lower center of the screen is a pressure-sustaining valve. The white arm indicates the slow rotation of suction scanner. Exhaust water leaves from the other side of the screen on the upper left-hand side. The whole process takes about 15 to 20 seconds. For low-pressure installations, the backflush mechanism must be rotated using an electric motor, as seen here. An electrical pressure differential switch is used rather than a hydraulic switch. With automation, these units can be effective in very dirty water conditions. The next devices are used primarily for well water. However, they are also found in some surface water situations.
The sand separator operates off centrifugal action. The water comes in on this pipe off the discharge of the pump, enters the unit tangentially at the top here. The centrifugal action begins and moves that sand to the perimeter of this chamber. That sand then falls and collects in this lower chamber. Back up in this area, that outward centrifugal action creates a low-pressure vortex. That vortexing actually provides an outlet for the water, which discharges out this middle pipe, out the top, goes onto the system. So you're basically coming from your water well or from your water source, removing the sand and grit from that water, sending clean water onto the irrigation system. Material collected down in this chamber can be flushed either manually or automatically with a simple actuation of a valve. Now, of course, it's coming back into the demonstration unit here. Normally, this would flush out to a waste site or to some other area for disposal. As the particles are separated, they fall off of a spin plate located in the collection chamber. That spin plate not only allows for the quiet accumulation of the particles, but also provides a place for the vortexing water to turn and discharge out the top of the separator.
If they are sized properly, these devices will remove somewhere between 70 and 95% of the sand. They do not remove clay or silt, nor do they remove organic material. Sand separators must always be followed by some type of screen because they do not remove all of the sand. There must be enough flow rate through a separator to cause sufficient swirling and centrifugal action. Generally, there must be a minimum 5 to 6 psi pressure drop across a separator. Therefore, it is difficult and often impossible to select separators to work well under a wide range of flow rates. If a flow rate changes with time, another option such as media tanks might be necessary. Other filters combine a screen with the action of a sand separator. Such filters may use a directional nozzle plate which directs incoming water onto the inside of the screen. A head loss occurs across the spin plate when the water changes direction and accelerates the solid particles to the outside edge of the tank. Holes in the spin plate are manually plugged if the system flow is less than optimum. A pressure drop of at least 5 psi is needed across the filter. Enough holes are plugged to obtain the required pressure drop. The spinning motion by the water pushes the debris to the bottom of the tube, where a valve allows several gallons per minute to continually drain water and dirt to the atmosphere. These designs with internal screens and water jets should not be used if the sand is very hard and angular, as the fine inside mesh screen material can be destroyed by the abrasive action of such sand. There are many other types of filters. For example, this screen is designed so that the incoming water flows upward and the sand falls down to the bottom sides, keeping the screen relatively free of sand. In summary, there is a wide variety of filter designs available. Most filters are designed for a limited application. Others, such as media tanks, can provide filtration for a wide range of conditions, but only if they are sized, adjusted, and maintained properly. For more detailed information, the Cal Poly ITRC has published a book on drip and micro irrigation. It has also produced another video on media filters.